Okay, so this week we're learning all about phylogenies and how we infer evolutionary relationships among organisms. One of the key tools we're using for that is what's called the coalescent simulations, where we try to look at a set of present-day organisms and see how they are descend from a common ancestor. So we're going to use a really simple simulation here to sort of establish the principles, and then you'll do some more complex simulations on the computer. So what we're looking at here is, imagine we have a really simple population of 8 individuals. So this is basically a family rather than a really big population. And this is the present day. There's 8 individuals, and they all descend from a common ancestor at some point in the past. So what we're going to do is use simulations to track their genealogy and see how they descend from a common ancestor and when that common ancestor might have lived, which is when all of these extant individuals coalesce, which is why we call it the coalescent. So for simplicity, we're going to imagine these are basically bacteria that have a single parent with a descendant rather than biparental inheritance like in people. Same principles apply, but it's simpler to think about it this way. So you can think of each of these as an individual that has a chromosome with one locus in it that we're going to focus on. So all of these 8 pennies, we've had them all the same color because they all descend from a single common ancestor at some point in the past. So now this is the generation before, and we're going to draw the connections of how these pennies in the past are related to these pennies here. We also have a couple quarters, a different color, to indicate lineages that have no living descendants in this population. So we can imagine one individual like this one is descended from a single individual in the past. So this individual had one descendant that made it to the present day. Other individuals like this one might have had 2 descendants. So we represent it with 2 lines. Another ancestor might have had no descendants, so it has no lines connecting it to the present, even though it's still a penny because it has a common ancestor at a time in the back. And so we can fill that in for the rest of them. So this individual had 3 descendants, and this individual had 2.
Add another quarter.
And now we'll keep going back further generations. So again, now we have a situation where this individual had 1 descendant, this individual had 2 descendants, this individual had none, and this individual had 1 descendant. And then we have 4 individuals that have no living descendants. So now I'm going to fill it in until they all coalesce. So what we can see is that all of the present-day individuals coalesce and share a common ancestor that lived 1, 2, 3, 4, 5 generations in the past. If I've done this right, there should be, I think I'm missing 1 coin. There should be 8 individuals at every single time step. So this is a constant population size. We'll look at examples where the population size changes, but it's easiest to understand it when there's only a single population. I realized I had 1 individual that had no parent. But for simplicity, we'll look at constant population size first. So what we're looking at 5 generations ago is that at that time there were 8 copies of this 8 alleles, copies of an allele at this locus, whatever locus it is that we're looking at, and there's only one copy that gave rise to all of the descendants that we see around today. And there were 7 other copies that had descendants, but those lineages eventually died out before reaching the present day. And so we refer to this as the coalescent process because we're looking at how all the present day allele copies coalesce at some time in the past and the relationships through